Hello and welcome to this lecture on a description of the project that we require for this course. This is the main project, and I'm going to introduce the connecting rod project and the different steps that we're going to take in order for us to fulfill the requirements. So for this lecture, we will cover the connecting rod project requirements, and I'll describe to you the steps and some of the details to give you an idea. And then I will conclude with a discussion of the grading requirements. So the connecting rod is a very essential component in all internal combustion engines that have many applications. The application we're going to choose is automotive. As we discussed before, there are a very wide range of applications of internal combustion engines in every aspect of mechanical engineering. So let's focus here on automotive design. So in this case, we have an internal combustion engine producing power, and the power is contained in the cylinder. And once we have a spark plug that ignites combustion, the combustion process will push the cylinder down in a linear up and down motion. So the connecting rod was invented maybe 1,000 years ago or longer. You can do some research to find out the history of the connecting rod. People, by just natural experience, they found that if they introduce a rod that connects a region that has linear motion up and down, then this rod will convert the linear motion to circular motion, revolutions that can drive things to move on a wheel. So it was a very great invention. So here, in terms of the engine, the piston is the component that has the pressure from the combustion process. We will give you how to compute the pressure will be also part of the process for the engine that you'll choose. And the piston is attached to the small end of the connecting rod. We have a small end here, and we have a large end here. So the small end is connected to the piston with a pin, and then we have the rod in between. And the rod now is attached to the crankshaft, and the way it is connected to the crankshaft is in two pieces usually. One half a circle here, half a circle here, and then with two bolts. So when you add them together, then you would get that shape of the connecting rod. And that's the subject of the project. So the requirements for the project is that we want to design minimum weight. So it has to be the smallest weight, because the weight is always related to manufacturing cost. And for the internal combustion engine, you choose an engine for a car of your choice. Some cars are designed to be very powerful, but they don't have to last for a very long time. So in this case, you have very high-end cars, very high horsepower, and then a lot of internals can be changed if it is a racing car, for example. Or if it's a passenger car, then the design is quite different. The requirement is almost infinite life for the components, or very, very high mileage for the components these days. And the first thing you want to do is find information on the engine characteristics, which is a relationship between the value of the torque, that's the forces on different parts of the engine, and the RPM. and usually there's a peak value for the torque at a given RPM, and that's where we want to design, because that's a critical combination of RPM that produces forces on rotating machinery, very high forces, and also the torque, the high torque can introduce additional mechanical forces. And then we're going to go through steps. So the first step is load analysis. So we will identify the pressure coming from the cylinder, the forces between the piston and the rod, PR, the forces between the rod and the crankshaft, RS, S is shaft, so we have two ends. And then the rotation, because of the RPM, is going to also produce loads that are inertial. So we have mechanical loads emanating from the pressure, and the pressure is bucked or supported by the rotating crankshaft. So that's in the two ends. And in addition to this, the revolutions themselves produce centrifugal forces that need to be also included as what we call inertial forces. So that's kind of a summary. And then once we have done that, then we will take these forces and do preliminary beam analysis. So we can consider the rod as an ideal beam, and the ideal beam would have forces on all the different ends and inertial forces, and then we'll take that and then analyze it as a beam using beam theory, which we all should know. And then once we have sized it by hand, which is an important step in design, is hand calculations first. We have to figure it out within, say, 30%. We should know the answer within 30% using hand calculations. Once we've done that, then we can take it to the computer. And in this case, we're going to do a solid model. And a solid model, we would do a 2D solid model using elastic finite element method. And then once we have that, then we will try to minimize the weight by doing fatigue analysis, fraction analysis, and satisfy the ASME code for design. Now, if we have very large values of the factors of safety, then we have to backtrack and reduce the weight, make it smaller until we meet the minimum allowable factors of safety by the American Society of Mechanical Engineers. Once we've done that, then we would do several optimizations to improve the design by variations of key configurations and key dimensions of the connecting rod. We settle on a final configuration, and that will be towards the end of the quarter. And then we move on to do a three-dimensional solid model and take that solid model and introduce it into another finite element system that we would use to do three-dimensional analysis. So that's kind of the general procedure. The connecting rod looks like this in general. We have a cylinder connected to the rod, and you can see it kind of carved out in the middle area here. And the reason it's carved out is that you try to minimize the weight. So it's similar to the idea of the I-beam. You don't need to have a lot of volume everywhere in the I-beam, so you just cut out the middle part of the I-beam, because the moment of inertia that resists bending is proportional to the depth cube, and therefore the depth is very important. The width is not that important, so you can cut it back into the middle. And that's what happens here. And then you have the two bolts that connected to the crankshaft. Now, in do 3D modeling, we not going to produce detailed models for the bolts because that will take more time and more detail to do the stresses and the distributions of forces and so forth on the bolts, and therefore we're going to take it as a continuous system, as you can see in here. Here are two examples. The connecting rod has either an I-beam shape or an H-beam shape. So the I-beam is the standard. You carve out the middle part, and this looks, if you take the cross-section and you cut it across here, it would look similar to an I-beam. So if you take a cross-section, this case, then the cross-section of the rod is going to look like an I-beam, and that is the cross-section here. There's another possibility, and that you'll find in many connecting rods, is an H-beam, and the H-beam is like this, just looks like an H, and the cross-section is shown here. So again, the idea is reduce the weight by carving out some part of it and hope for the best. Now, the objective of the course is to learn about material behavior, mechanical behavior of materials as it pertains to design and how that influences the failure. And we'll see that failure can occur by a variety of means, either steady state or time-dependent fatigue. But at the end, it manifests itself as a fracture or separation or extreme deformation. Even if it doesn't fracture, you have extreme deformation. In this case, you have extreme deformation, so the rod is not going to function, obviously, even though it didn't break. Here you have fracture on the small end. Here you have fracture on the big end. Here you have fracture around the bolts. So the fracture can happen anywhere, depends on the types of materials used, the dimensions, the design aspect of the rod, and therefore we have to go through our analysis in critical locations to determine what is going to happen. So we will learn also a number of very useful tools in this course. So the tools are going to allow us to be more professional in our determination for design procedures and requirements. And the first thing we want to do is hand calculations. And I didn't mean it literally hand calculations. Of course, you can do something very quick, but the way to do things now is using MATLAB. So many of you have used MATLAB before as a calculator. So you just make a small program. We will introduce a few programs to you at various steps, and these programs are either half-written or guided, so you'll be able to do your evaluations before you get into finite element solutions. Then we also will learn how to use SOLIDWORKS in this course. Some of you have already known that. Some would have to take a refresher in SOLIDWORKS to produce a three-dimensional. 2D is very easy, or 3D. So SOLIDWORKS will be an additional tool that will be learned. We also will do most of the analysis on COMSOL, and the analysis will be in 2D FEM analysis on COMSOL. That is a very good platform to solve partial differential equations that describe elasticity, heat transfer, fluid mechanics, all kinds of physics, continuum physics in general. For us, we would just use structural mechanics module in COMSOL and do the 2D finite element analysis. Of course, COMSOL can also do 3D, but we will attempt to do the 3D to add a little bit more experience, if possible, with Abaqus. So the use of Abaqus is kind of optional in a way. If you could use it, it will add to your arsenal of tools that you can put on your resume. If it is not possible, then you could continue using SOLIDWORKS and then import from SOLIDWORKS into COMSOL directly as a 3D object. Now I'm going to spend a little time on the first subject, which is force analysis on the connecting rod. So the connecting rod is the rod that connects R to P. These are 2 points, you have R and P. P is attached to the piston, so the piston is here, and the piston is going up and down, and therefore point P can go only up and down. So it's constrained motion of this node or point P. R is attached to the crankshaft. So the crankshaft is, the center of the crankshaft is here, and the crankshaft, it rotates, and it rotates 2 cycles for every 4 strokes. So we have the 4 strokes that we discussed for the engine result in 2 cycles. Each one is 360 degrees. So to describe that rotational motion, we use an angle phi. So phi is used here. This is lowercase phi. And lowercase phi goes from 0 to 360. And you note now, because of the constraint of P, that the angle between the vertical Y and the rod is gamma. So gamma here is related to phi. It's not exactly phi, so we describe the main motion as phi, and then the linear motion is described by this angle gamma, and we note that phi dot is the angular speed, which is the RPM omega, and phi double dot is omega dot. This is the acceleration, angular acceleration. So we have to just keep in mind. Now, for our design for this rod, we're going to look for steady motion. So we're going to design it at the peak conditions, which is the peak torque and RPM combination, and assume that it's going steady at that rate. So there's no acceleration. And in this case, omega dot is equal to 0. So we're going to design it for phi dot equals omega equals a given RPM, and that will be included into the analysis. So going back to the rod, we have now to describe the connecting rod with vectors. So we have one vector from the origin O to R, and this R, capital R vector, is, we have a unit vector along the x direction is I, the standard, and the unit vector along the j direction is, along the y direction is j. And therefore, if we want to describe capital R, then we have to go 2 steps. We have to go backwards here, which is minus R sine phi, and we have to go up, which is R cosine phi in the j direction. So a few steps in the I direction, a few steps in the j direction, then we get the vector R. The vector P is all in the j direction, and it's made up into 2 pieces. One piece is this piece, and then another one is this piece. So you have this two parts of the describing the vector p, which is in the j direction. Now I have to consider some geometry. Lowercase r is the radius for the crankshaft. L is the length of the connecting rod. And then R over L is a ratio that we're going to call lambda. So it depends on your design. And now the connecting rod itself has another ratio beta, such that beta times L determines the CG of the connecting rod, the center of gravity of the connecting rod. When you do the 3D model and you import it into, or you create it in SolidWorks, it gives you the geometric properties, including the center of gravity. And that's important to find out, because as a mass distribution, we will assume that the whole mass of the connecting rod is centered or focused on that point. And that point is described by the value beta, such that when we multiply beta times L, we get the position G, which determines where the center of gravity is, and this is where we're going to introduce the inertial forces. So the G is a linear combination of R and P minus R, and the linear combination, or basically of P and R, we have a linear combination with this beta. So beta times P plus 1 minus beta times R, because the two vectors, we get a linear combination. This is a convenient point to stop, and we will just continue our discussion of the connecting rod project, where we're going to talk about dynamics, we're going to talk about finite element optimization, and the grading system. So with that, we will finish this video, and I hope to see you on my next video, and thank you for watching.